Where Are You, Delphine? The Story About the Blue Rose by Jillian Guiyang, Jewel Liman, Angela Lamas, Martin Rantutar, and Gabe Saison. On June 2004, Suntory Holdings Limited, a Japanese consumer product company, and Florigene Flowers, a biotechnology company based in Australia, announces the successful development of the Blue Rose.
Sir, how were you able to develop the blue rose? We used a blue color from another flower.
We genetically engineered it.
Well, how many years did it take? A total of 14 years.
It started in 1990 when Suntory and Florigene worked together.
Wow! So why did you choose to make a blue rose? We wanted to make the impossible possible.
The real reason why?
Mr. Katsumoto returns home to his daughter's tomb.
Happy birthday, my daughter. It's been 14 years. Delphine, do you still remember? My daughter! Delphine!
Due to intense grief, Mr. Katsumoto falls into a deep sleep.
Huh? Where am I? Mother? Is that you? Am I dead?
No, my son. You are in the underworld.
What? How?
Delphine, your daughter. She needs your help. The Emperor plans to trade her off to the King of the Underworld to pay for his sins. Once that happens, she will be trapped in his palace forever.
Can I save her?
There is one way, but it's impossible.
Tell me, I will do it.
You have to find a blue rose, the symbol of death and rebirth. It will open a door for her to cross from this world to your world.
Mr. Katsumoto wakes up and was convinced that he must find a blue rose to save Delphine.
I need to find the blue rose. Are we up for a challenge?
Such as...
Let's make a blue rose.
Interesting. We'll need collaborators for that.
Florigene Limited might be willing to help out.
There are two things we must do. Isolate blue genes from other flowers and develop a way on how to put that in the rose.
Alright, how about let's start with petunias? There's a lot of available information about their pigments.
Going back to 1991, they were able to isolate the blue genes from 300 candidate genes from 3,000 genes of the petunia and immediately patented it. The next step is the method to produce the gene vector into the plant.
The scientists now had to isolate the ripe petunia gene from 300 candidate genes of the total 3,000.
I think I have done it. I have isolated the right gene. My next step involves introducing the gene for the blue pigments into the rose, but this may take a while.
After 3 years...
I have inserted the blue pigment gene into the DNA of the rose, but something's wrong.
So how did you insert the gene into the rose anyway?
I used Agrobacterium, a soil bacteria, since it cannot carry its own genes into plants. I have selected bacterial cells that have received the genes after transferring the blue pigment genes. These are then transferred and regenerated into the rose's body.
Firstly, the plasmid is removed from the bacterium, and the tDNA is cut by a restriction enzyme. Then the foreign DNA is cut by the same enzyme. The foreign DNA is inserted into the tDNA of the plasmid. The plasmid is reinserted into a bacterium, wherein the bacterium is used to insert the tDNA carrying the foreign gene into the chromosome of a plant cell. The plant cells are grown in a culture. And then lastly, a plant is generated from a cell clone. All of its cells carry the foreign gene and may express it now as a new trait. In 1994, roses with blue genes had appeared, but still there was no blue pigment that manifested.
We should select cells that have received the genes after transfer and regenerate them into the plant body of roses. So we have to make as many genetically modified roses as possible. We should perform tissue culture, a procedure done in sterilized conditions using a plant in a test tube.
In the case of roses, it takes about a year from the introduction of genes to the blooming. The effectivity of the introduced genes to function differs from one genetically modified rose to another. In 1994, roses to which two kinds of blue genes of petunia has opened. However, the flower's color was still red and no blue pigment was detected, although the genes have already been introduced.
We have been conducting this research for over 4 years now, and it seems that no blue rose still manifests from our experiments.
What if we try to introduce blue genes other from that petunias?
Let's try gentians, butterfly pea, and torrenia.
However, no matter how many times they have conducted experiments, only roses with blue genes, but without blue pigments, bloomed. After several experiments, the blue gene from the pansy was able to produce the blue pigment from rose.
We've tried extracting the blue genes from petunias, gentian, butterfly peas, and tornea, yet none of them are able to grow roses that manifest the blue pigment.
We've been trying for so long, what else can we do? Maybe we should just give up.
Don't lose hope. If genetically modified blue carnations are possible, so are blue roses. We just have to think of more organisms with blue genes. What about pansies?
I guess it could work. Let's try it.
The scientists begin to experiment, this time using pansies as their source for the blue gene. After several trials, they were one step closer to what they sought after.
The roses! They changed color!
Wow, I can't believe we did it!
The roses did indeed change color, however, they turned dark red.
This is mainly due to the original characteristics of the rose we introduced the gene to. For example, if it is acidic inside the cell vacuoles in which the blue pigments are accumulated, the color will remain red. However, if it is neutral, it will turn blue.
Based on observations they made from the prior research they conducted while working with violet and blue flowers, the scientists realized that flower color is mainly determined by the anthocyanins. Anthocyanins are vacuolar pigments found in flowers and plants. The color expressed in plant is dictated by the pH value of the vacuole they are in. The color is bluer in neutral to basic pH and redder in acidic pH.
Also, the existence of the blue pigment or gene does not automatically mean that the rose will turn blue. It still depends largely on the components that enhance the blue can or cannot exist in the vacuoles.
So, what do we do now?
We must choose varieties of roses that can most probably lead to the manifestation of the blue color, even those that are not commercialized.
We can also improve our tissue culture so that it may be introduced to many varieties of roses.
Okay, let's do it.
The scientists then proceeded to gather many varieties of roses that would likely result in the accumulation of a high percentage of blue pigments and a more bluish color. There were plenty of roses to choose from, but the hosts had to fit some criteria so that the F35H gene, or the blue pigment, would be expressed successfully.
Firstly, the host should accumulate lots of flavonols.
Their vacuole should also have a higher pH value. Let us avoid anything acidic.
At this point, the scientists were already on track on how they will make that blue rose bloom. Flavonols are colorless molecules that enhance the color expressed by anthocyanins, or the pigment-producing enzyme. Red flowers have fewer flavonols than blue or violet flowers. Bear in mind that blue flowers have vacuoles with a neutral to basic pH value. This is important because even if a flower has blue pigment, if its vacuoles are acidic, it will still end up colored red.
We should also avoid any cultivars that might have the F3H gene or the enzyme to produce red pigment.
F3H genes are the key enzymes that help produce cyanidin, the red pigment. Meanwhile, F3-5H genes help plants produce delphinidin, the blue pigment. Because of the criteria, dark and red roses were avoided because of their low pH values. Yellow and white roses were avoided because their petals did not accumulate any flavanols. As a result, pink and mauve-colored roses were chosen as hosts for the gene. 169 cultivars, short for cultivated varieties, of roses were chosen for further testing.
I think now's the time to run some tests.
I'll start on the flavonoid analysis.
I'll work on getting each one's pH measurements. We should now induce the blue gene, or the F3-5H, into the calluses of the host we picked out and see how it will affect a flower's change in color.
Callus, or calli, are undifferentiated cells whose functions or morphology has not been determined yet.
It seems like overexpressing the viola F3-5H gene will not be enough to make the roses blue.
The rose DFR gene, naturally found in the chosen host roses, has a competing reaction with the blue pigment gene, or the F3-5H, we are introducing.
The rose DFR gene had a characteristic, namely substrate specificity, that determined which anthocyanidin, or the plant pigment, a plant accumulates. The rose cultivars did not mainly accumulate delphinidin, or the blue plant pigment needed to make its petals color blue.
I have an idea. What if we suppress the rose DFR gene and introduce the DFR gene of a flower species that mainly absorbs delphinidin instead?
Let's try the one from irises.
By overexpressing the F3-5H gene that produces delphinidin, or the blue pigment, and by introducing the iris DFR gene that accumulated mainly delphinidin instead of other anthocyanidins, also known as the plant pigment, a transgenic blue rose was made.
The results are astounding! 9,596 accumulation of delphinidin in these roses. Can you believe it?
Don't celebrate too soon. Let's graft these roses to see if they will actually propagate stably.
And true enough, through grafting, they were able to confirm that the blue phenotype of the transgenic rose is also inherited. The blue roses grew stably and normally. Mr. Katsumoto places the blue rose on his daughter's tomb. A few moments later, the door into the underworld opens and frees Delphin's soul from the treacherous prince. Since then, they named the blue pigment of the blue rose delphinidin, in honor of Mr. Katsumoto's daughter named Delphin.